Okay, so thank you very much, and I want to thank the organizers, of course, for the opportunity to come to this really incredible place. I had a great time so far. So, yeah, I will talk about some asymptotics in non-Hermitian ensembles of random matrices. So these will be basically planar models, so random matrices with eigenvalues in the complex plane. So it will be one of the distinctions with previous talks on random matrices. So the goal, or what I would like to sort of talk a bit about, are certain correlation functions of characteristic polynomials. So again, the characteristic polynomial will be the main object. So we'll take a product of m different powers of the characteristic polynomial of some random matrix Gn. And each of these characteristic polynomials will be raised to some exponents, gamma I, and positions zi. Okay. And what I'd like to talk about are some asymptotics. Asymptotics of this type of quantity as n goes to infinity. So n here is just the size of my random matrix. So let me start by just saying a bit about what kind of matrix I take here. So I will look at the essentially most classical example of a non-Hermitian random matrix. Okay, so, these are the ones after Jean Genibre, who introduced them in the 1960s. So Genibre random matrix. If you like, it's a direct non-Hermitian analog of the Wigner-Dyson symbols. So you have GUE, but now we have Genibre UE, if you like. So Gn will be 1 over square root of n times a fixed matrix G. So G does not depend on n. And it has complex normal entries. So I have normal random variables in this matrix and no assumption of hermiticity or any kind of symmetry. Okay, and they are all independent, identically distributed random variables. Okay, so they have mean 0. Expectation of each matrix element is 0, and the variance is normalized to 1. So I hope everyone can read, even at the back, hopefully can read writing. And so if you just go onto your computer, you go onto MATLAB and just generate these kind of matrices. It's very, very easy, kind of one-line piece of code. Then you will see that actually they sort of all fall inside a disk. You can see that it's on MATLAB in about 5 seconds. So you have all these eigenvalues. So these are eigenvalues of matrix Gn. And this turns out to be a disk of radius 1. So this is already quite a fascinating phenomenon, in my opinion. Of course, there are some eigenvalues outside this disk, but it turns out that asymptotically, they will cover the interior of this unit disk uniformly. So this is unit disk radius 1. And in mathematics, this has been the subject of quite a lot of interest. So it's known as the circular law. But for the purposes of this talk, I just want you to pay attention to the fact that something interesting happens as you get to the boundary. suddenly you have no eigenvalues asymptotically if you go outside the boundary of this disk. Yes, exactly. So if you rescaled the variance in some way, then you sort of change the radius of the disk. Exactly. Okay, so also say a bit about what I mean, roughly speaking, what I mean by critical. So I have these points at I in this main object that I want to consider, these determinants, characteristic polynomials. So something about what I mean by critical. So the main sort of example that I want to consider actually is just in the very simplest case of this correlation function. So I'll actually talk more about the one-point function of this ensemble. So for example, for m equal to 1, where this product just has one term, I'd like to think a bit about the case where z is close to the boundary. My argument here is close to the boundary. So this is what I mean by being critical. So z equal to 1. And there is a small window around the point 1 where there's a similar asymptotic behavior. So this turns out to be of order 1 over square root of n. This 1 over square root of n is just basically the mean separation between these points in the unit disk, order 1 over root n. Okay. So some motivations for studying this type of correlation function. So one of them is that, so if I call this star, okay, so this is kind of the Gaussian multiplicative chaos motivation. So you can think of star actually as a kind of Laplace transform of some kind of random process. So it's the kind of multi-point Laplace transform. Just to give you an idea why anyone would look at these correlations. So it's the expectation of this exponential, right? So it's the Laplace transform of a process. And this phi n is precisely the object which was considered in the last talk, okay, now in this sort of planar model. It's the log determinant of Gn minus Z. And so, of course, this process is believed to converge to a log-correlated random process, or in some cases proved, or in some interpretations of the convergence. So if I tell you that this converges as n goes to infinity to some limiting process, this will be a log-correlated Gaussian field. And for results in that direction, there is a quite famous paper of Ryder and Virag from 2006 on this topic. So basically, what we would expect, so I don't claim to prove that in this talk, is that if you look at e to the gamma phi n and normalize by the expectation, then this should converge in some sense to the multiplicative chaos that we saw, this time the two-dimensional version. Okay, so I want to start by stating a theorem that's in the literature at the moment that sort of also partially motivated us to look at these questions. So there's a theorem which is literally just about the one point function of this correlation function. And that sort of tells you a bit how slow the progress has been, actually. So, I mean, Genebra introduced this ensemble in the 60s, and, 2017. So let real part of gamma greater than -2. So I can take, in this theorem, quite a general gamma. I take a delta greater than 0, which will be fixed. And then I look strictly inside the unit disk. And then these authors, Webb and Wong, they have a asymptotic expansion for just one determinant. So here's how it goes. So there's essentially 3 terms. So here's the biggest term, which is linear in n. It's perhaps the least interesting term in some sense. Then there's a more interesting term which is quadratic in gamma, which grows like log n. And then, as usual in these random matrix asymptotics, there's a constant term, which is often of interest. And then you have subleading corrections. So I should tell you. Sorry, it's a multiplicative. This is 1 plus something smaller than. Sorry, yeah. Yes, sorry. Okay, so we have this constant term, and that's sort of what I'll be interested in telling you about in this talk a bit, or how that changes. Yes, exactly. So G is the Barnes G function. So basically, in this constant term, you often pick up nice, exciting, I think, different types of special functions. So this Barnes G is often appearing. So not Barnes G function. So if I tell you how it behaves on the integers, it kind of gives you an idea. So it's a product of factorials. But there is a way to define this thing on the complex plane. So there's a kind of functional equation. So it sort of is generalizing the gamma function. Okay, so the main question I want to ask, at least to start with, is what if Z is approaching the boundary of the unit disk? So what happens? So Webb and Wong are assuming that this Z really stays strictly inside the disk. Is it true that the asymptotics just continue to hold uniformly? So it turns out that's not the case. So the restriction they have is really sharp, and a new behavior comes. So this turns out to be related to the GUE, actually. So one of the things that we've looked at is how these asymptotics for non-Hermitian ensembles, there's a connection to the standard Hermitian random matrix theory we're used to. So GUE of a Hermitian matrix, and it's going to be a K by K Hermitian matrix. So this is just a matrix of Gaussian variables again. So it sort of has a density e to the minus trace h squared over 2. This is a GUE random matrix. And what will play an important role is the following function, fkx is the probability of the, well, it's the distribution function for the largest eigenvalue of h. Okay, so now I'll present basically the main theorem I want to state. So this is with my collaborator Alfredo Giano. And okay, so what we can show is that for this one-point function, so one of the main differences is that actually we start with looking at basically integer exponents of gamma. Yes, so so is a k here as well. So H is a k by k GUE matrix, and it's the same. It's going to be the same k which is here somehow. Okay, so basically, what we find is exactly the same kind of structure. And what really changes is the constant term. So there's a second part, which is this function f. Square root of n times 1 minus absolute value of z squared, and some error, and then basically this is uniform. So what we can say is that this is holding uniformly on the disk, and so it's important that I've taken k to be a natural number. So to prove this rigorously, we have to assume this at this point. It's fixed. It's fixed, yes. Not with our technology at the moment. So it should be if you take a limit with k growing as well, there should be a relation to the Tracy-Weedham. Yeah. So just to comment that you can see the reduction to the previous result if you're not too close to 1, right? This thing will go to plus infinity, and you're looking at the probability that this will go to 1. But then there will be some scales of z where it's non-negligible contribution. So you can see that you have this critical scale where the modulus of z is 1, and then something of order square root of n. And then this term you will need in the asymptotics. This can be written as a Fredholm determinant, that's right. Actually, the other thing, the reason we kind of like this formula, so remark, So the largest eigenvalue of a GUE random matrix is somehow well-studied object. So you know for large size GUE matrices there is a Panlevey, a formula in terms of Panlevey transcendent. And actually it's true for finite size matrices too. And this was due to Tracy and Weedham in '93. So they found the following representation, that this function fkx is an exponential in some integral of this function sigma k of s. And the important thing is that sigma k of s actually satisfies an equation, a differential equation. So here's the equation, which turns out to be a nonlinear differential equation. And is better known as Panlevey 4. Or it's closely related somehow to the fourth Panlevey equation. And for the purposes of wanting, let's say we want something similar to here where we have a general real exponent, then what we kind of strongly believe is that, which we have not proved yet, is that you can continue this parameter to something real and that it still gives the correct behavior. And last thing I want to remark, so a second thing, is that there is some overlap with a very interesting work due to Nishigaki and Kamenev, which is kind of more from the theoretical physics point of view, from 2002. And this is by supersymmetry methods. So they also observe some relation to to this GUE probability. It's a very interesting paper, actually. Okay, so there is an approach where people in the audience are much more knowledgeable than I am about this. But if you have integer, say two times an integer powers in your characteristic polynomial, you can sort of expand these determinants in terms of Grassmann integrals, basically, and then you can try to do a saddle point calculation. Okay, any other questions? That's probably it. Must be a typo. Yes. Yeah. Thank you. It's a typo. This should be gamma over 4. Yes. Sorry. Any other questions? Okay. So we'll talk just a little bit on the approach, which I think is also kind of interesting. So it's a very different approach to this work. So it's by determinantal structures. How much time do I have? 20 minutes, okay. So if I look at the distribution of eigenvalues in these Genebra ensembles, so actually, even in Genebra's 1965 paper, he was able to write down this joint law explicitly. So let me give you that. It's very, very explicit. So here, v of lambda in the Ginebra case, I mean, will just be quadratic, just the kind of Gaussian character of the distribution. And then, of course, there is this interacting part. So squared van der Monde factor. So let me tell you what this is. So this delta of lambda is just the product of all differences of the lambda 1 up to lambda n. And so if you want to calculate some expectation value like this, then you're talking about doing some n-fold integrals over this this measure over the complex plane, basically. There is an approach that also goes back a long time, mainly due to Dyson, Mehta, and colleagues from the 60s, that tells you that the way to proceed with these kind of joint densities is to introduce a family of orthogonal polynomials. So the determinantal structures, they come from rewriting this factor, right? So it's determinant lambda I to the j minus 1. I and j go from 1 to n. So that's a way of rewriting this product of differences as a determinant. And the idea is that instead of using these monomials, we should use some suitable set of orthogonal polynomials. So I look for polynomials which are orthogonal with respect to this weight, delta jk times some normalization. And then it turns out that many of the statistical properties of this distribution, these kind of averages, you can at least make some progress with. So the important object is the correlation kernel. So it is a function just of two variables which kind of characterizes statistical properties of this ensemble. And it's just constructed from the orthogonal polynomials. Pj. And it's kind of a nice thing in the planar case that if you're v, so for us v is just absolute value of lambda squared. Whenever your weight for your orthogonal polynomials is radial, so it just depends on absolute value of lambda, the polynomials are very simple to guess. So actually they are just monomials. So that's quite good progress. So for Ginebra, and in fact a lot of models, you already have the orthogonal polynomials. Just a side remark. So the main approach we employ, as opposed to kind of supersymmetry methods, is a formula due to Ackermann and Vinizzi, 2002. And this, so this tells you how to compute correlation functions completely separated, so no powers, basically. So if I take a product of determinants, sort of like I did at the beginning of the talk, and I take the Hermitian conjugate in the second determinant, then this has a very explicit and beautiful expression. So this turns out to be exactly equal to some product of normalizations, which is somehow easy to deal with, and then a term which is less easy, but looks a lot nicer than the multiple integrals we had before. So it turns out to be a kind of ratio of determinants. So it's this determinant involving the correlation kernel. Then there's a denominator, which is van der Mon determinants. And so the hard thing is somehow to figure out how to merge points, right? So if I want to get something, say I want the 1 point function, so just one determinant, then I have to take all of these z's and w's equal. But then, of course, these are 0, and then I have to do something. So I look for this kind of limit. And so basically we have some way of understanding this merging. But first I just want to show you what you can do if you just try to find the asymptotics for large n and see what you get from this Bn. So we can write the kernel straight away. So it's a sum. Just of these monomial things. So if you compute these hj, these norms, you just get j factorial. And so because I'm at the edge, I want to scale x and y in a certain way. So I want them to be close to 1. Then actually I can give you the asymptotics for the kernel. It's kind of well-known thing. So you get some kind of simple exponential prefactor. So this exponential thing is a bit like the main large sort of exponential terms in this theorem. And then there's a term which doesn't depend on n, so this contributes to the constant term, and it's a complementary error function. Okay, so in principle, we just have to compute the determinant of this Bn, or otherwise the determinant of this complementary error function. Okay, so I have a lemma in that direction, which turns out to be related to surprisingly somehow to us, to non-intersecting paths, or non-intersecting Brownian motions. So I'll write PT to be the transition density of a standard Brownian motion. So then I can tell you, roughly speaking, what the determinant of this thing looks like. So determinant of A of Ui and Vj turns out to be equal to a multiple integral containing a product of two determinants. Sorry. Yeah, good point. Thank you. So A is this part here that we somehow have to compute determinant of. So here again, I have a second determinant of the same, basically the same function, and then I integrate over all these x's. So this structure, so this product of two determinants, is kind of well-known object somehow. Exactly. So it's coming from Carlin-McGregor formula. And this is sort of appearing because I can write that function A of uv, which is a complementary error function, as an integral involving this transition density. So this product of two determinants, so it appears in the following situation. So I have k points, u1, u2, coming down to uk, and sort of k target points, v1, v2, up to vk. And what I'd like to consider are k Brownian motions conditions. So they start, so at t equals 0, they start at these positions, u1 up to uk, and at t equals 1, they terminate at these positions, v1 up to vk, and they're conditioned not to intersect. They cannot intersect, so they do something like this. And then you look at the midpoint, so t equal to a half, and record these positions, so x1, x2, xk. Then basically the statement is that the joint density of these points, x1 up to xk, is the product of determinants inside this integral. So this is Carlin-McGregor formula. And then it's sort of well known in study of these kind of Brownian motion objects how to merge points. So how you could start with just k Brownian motions at a single point. So I can try to merge these points, u1 up to uk and v1 up to vk. This is sort of going to be the final thing, that if I study this limit, as the u's all coincide and the v's coincide, I will get an integral of the following type. So j equals 1 to k, e to the minus xj minus 2u squared over 2. And then you'll actually get Vandermonde, squared Vandermonde determinant here. And this is just the GUE, basically GUE eigenvalue density, except for this shift, right? So this shift, I have to change variables or something, right? So I change variables, and it's going to go in here, and then I will get my, this is basically proportional to the probability that the largest eigenvalue is less than 2u. Yes, sorry. So actually, I've taken all of them to be u. So actually, I could also, I think what happens if I remember is that you get this u plus v if you do it separately. Okay, so my time is probably 4 minutes. Okay, so in the last time, I will just describe some slightly broader picture of this. Or what we think of as a kind of duality between non-Hermitian matrices and Hermitian ones. So I do a quick table. So n, which stood for the number of determinants I had. N was the size of my random matrix ensemble. And then I'll have a kind of type of duality. So just to summarize, if I took just one determinant to a power 2k, and I looked at large n close to the edge, then I'm getting this GUE picture, lambda max of GUE. So actually, turns out you can look at finite n as well. And there's another duality, which we can also access from this Ackermann formula. So it turns out not to be the GUE, but something closely related. So it's a product of two rectangular matrices, and they all consist of Gaussian variables. So this is called a Wishart matrix. So it's K by K Wishart matrix. And we also looked at the case of two. So this was an edge. This asymptotic one was an edge limit. So we also looked at product of two characteristic polynomials in the bulk. So asymptotic limit. And we look at Z1 minus Z2 being close, of order 1 over square root of n. And then it's also related to a largest eigenvalue distribution, which also turns out to be of Wishart type. Of course, it's asymptotic, so there will be no n in this. So it's just K1 and K2 corresponding to your Z1 and Z2. So this is the sort of picture that we have in the Ginebra case. And yeah, so finally I'd sort of like to conclude by saying we don't yet have a good intuition for how this duality is emerging. So if any more physically inclined people could maybe enlighten me how this happens, I'd be very appreciative of that. So I'll just leave it there, and thank you for your attention. So in this theorem, no. So this is only uniform on the